regression using our software. We're getting into the estimation. So we have prepared the data. Now these are the steps involved in building a regression. First we'll import the data. Then we'll clean the data set. Then we'll proceed to creating a training data set and a testing data set. The training data set is on which you build the model. And the testing data set is the data set on which you validate the model. Then you build a model. Finally, when the model has been accepted, then that becomes the model with which you make predictions. Then using the predicted values out of the testing data set, you measure the performance of the model, and then you fine-tune the model for further improvement. So first what we do in this exercise is first we divide the data into two parts. There are very many ways of doing it. There are many programs that do it. I will demonstrate one which way I have done it in Excel, in R. So there we are. So we're going to build a regression model. So we are importing the data from which we call DF. It's a corona data set. Then we look at the variables. And the variables are the province, the region, the latitude, the longitude, the date, the confirmed cases, the number of deaths per day, and the number of patients who have recovered. So now we have the data, and now we need to look at whether the data is clean or not. So for that, what we do is we will use some useful filters. One is we'll check whether any constant values, whether there are any columns with the same names repeated, so you can really get into that and try to correct it if necessary. So we won't really get into that. So we will straight away go about dividing the data into two parts. So we've read the data. We've had a look at the dimension of the data. We've got the names. The dimension of the data, it's got 16,884 rows and 8 columns. The names of the variables are these, which is shown over here, Then we split the data into two parts. And for that, what we do, so that the splitting can be recalled again in the future, we create what is called as a seed. We give a seed and 100, which means if we do this exercise again, we will get the same testing data and we will get the same training data. If we don't put a test, because since it's randomly decided, every time we may end up getting a different data. So first we impose a seed, okay. Not a function of seed, okay. I think that requires a program. So we will, for the time being, I will use that later. That will show you later. Okay, now this is what we do. First I create an index. First I create indexes. Sample 1 to the row of DF, that means how many rows it has. Then the size will be 80% of the rows. So I create an index. Then I split the data into I call it test.df, which is got by df into index. And then I will maybe get you the size of that file. That file is now 13,507, which is 80% of the total size. Then I create a training set. Sorry, this is usually a mistake. This should be the training. This should be the training. The larger sample becomes the training. Sorry, I made a mistake. The larger of the two. Okay, so the larger of the two, the training and the testing. So the smaller of the two will be the testing. So we test on a smaller sample. So we have the training sample, and then we get the testing sample with this command. And then we look at the dimension of the training, it should be 80%. And we look at the dimension of the testing, which is 20%. So this way you can change the proportions as you like by changing the command. But first you create an index, and then you say df of the index is the training, and then you say minus of the index gives you the test, which means that it will eliminate the cases in the index and keep only the testing. So we get the training period, and now we're going to build the regression. Now in this regression, we are going to have deaths as a dependent variable. Okay, so yeah, we're going to have deaths as a dependent variable, and the independent variables are the confirmed cases. Death is given the confirmed cases and the latitude. And the latitude. The name of the data is train, and it's going to be fitted. The command is very simple for regression. It's just an LM, and run it, and then we get the summary, and the summary gives us the results of the regression. So the regression is very easily done. You can recall a lot of procedures you have to follow before you got it there. Okay, so now we've got the thing. So all this is not required. Okay, so now we fitted a regression, and we got the results by pressing summary, and now we interpret the regression like this. The R squared, the multiple R squared is 0.77, which means 77% of the variation in the deaths is explained by the two independent variables in the model, namely confirmed cases and the latitude. And the effect is that about for every one confirmed case, there is, or in other words, if you have 100, I just multiply this by 100. For every 100 confirmed cases, you have 4 deaths. And keeping confirmed cases constant, every increase in the latitude will actually decrease the deaths. But this is not significant. Then we look at the significance. Confirmed deaths are directly related to the confirmed cases, but the effect of latitude on confirmed cases is not conclusive. Though it is negative, it is not conclusive. Okay, so this is how you build a regression. Now we've discussed elaborately on the properties of blue. So we need to test whether this regression is blue or not, right? So what we do is, we just have a look at the 3 properties. One is the independent variable should not be collinear. So for the test, first test is the test of multicollinearity. Test of multicollinearity. Test of multicollinearity, right? So test of multicollinearity, as we remember, the test that we used is VIF. Now to invoke the test VIF, you need a library called car. Right? You need that library. You have to install it if it's not already installed. Right? And then the command is very simple. You just say VIF, open a bracket, and just say fit, and run it. So confirmed has a VIF value of 1.003, and latitude has a value of 1.003 again. Right? Both are less than 8, and hence there is no problem of multicollinearity. So we've tested for multicollinearity. The next test is the test of heteroscedasticity. Heteroscedasticity. Test of heteroscedasticity. So we use the Bruce-Pagan test, and in case it's difficult for you to recall, just push double question mark and say BP test without a gap. It normally gives you it gives you an online help. It gives you an online help which you can use for this thing. So just scan through this until you get your Bruce-Pagan Bruch-Pagan. That's the Bruch-Pagan test. So to run the Bruch-Pagan test, you need to load this package called LM test, and the command for Bruch-Pagan test can be very easily determined from here. So you don't have to remember that. So you need the library. So you need the library. So I'll have to. LM test. Now this is the LM test I got from here. LM test, right? So to get that LM test. Okay. So LM test, I run LM test. Since I've already installed it, it's there. Run it once more. It's there. And then the test is calculated just with the BP test. Formula, by formula I mean this fit. By formula I mean the fit. Output file of the regression, fit. And all the other things I can leave out because they are not required to do the Bruch-Pagan test. So I just do BP test, and here I will write. Yeah. So the test is highly significant. So there is a problem of multicollinearity as a heteroscedasticity, and what the suggestions that were adduced in the previous class was either you build the model again, or you use the method, you use a Box-Cox transformation, or you will use the generalized least squares method. And the third test, of course, is not very relevant here because it's not strictly time series data. So we do not go any further into this model. So we need to test for time series because it's not time series in that sense. It's just that data that's arranged on time. Time does not have an influence on this, and therefore we do not go too much into the analysis. So this is basically what you would do with the regression. And before, suppose you want to know what are the variables that are affecting the regression, so normally they do what is something called pairs. So you get pairs of the variables you are interested in. So in order to get the pairs of the variables, pairs of the variables that you are interested in, so you are interested in this case you would have seen. So you are interested in variable 3, variable 5. You're interested in variable 3, that is latitude, then variable 6 and 7. So then what I'll say is, I will just say pairs df pairs. So the name of the file is train underscore df square. I want all the rows, and I want specifically these columns 3, 6 and 7. So if you don't use this, you will get too many graphs which you cannot really look at. So you can have a look at the figures and then decide you're interested in deaths. So you can see the relationship between confirmed and deaths is linear. But the relationship between, do it again. I think I've lost it. So the relationship between latitude is not a linear relationship. It is actually a Kirby linear relationship. So it's kind of goes up and goes down with latitude, but since it's I can actually use a squared term. So anyway, that I will not do. So now I need to validate this model on the test example. So my model is captured by this variable fit. So what I do is, so I just say predict. Then the model that I'm going to use is fit. The data that I'm going to use is test, not train. Test underscore df. Right? And I run the model. And it gives me all the predicted values. The predicted values of this model. Right? So this I can capture under in this file called test.tf. Dollar. I'll say predict. D. That's my new variable. So my new variable is in this file df. I have a predictor variable which is obtained out of this. In other words, what I'm doing, I'm capturing all this into a variable. Now what I'll do is I'll view it. View test. Underscore df. Test underscore df. Okay. So in this test underscore df, I will have latitude, longitude. What we are still modeling is the predictive, the deaths. And now this is predicting the deaths. And then what I will do is I will try to find out a new variable. I'll calculate out of that. I'll calculate mean average percentage error. I'll calculate mean average percentage error, which is equal to average. Sorry, mean. Maybe we call it mean of df $test divided by df $predict. So I will use pred. So here what I'm doing is I am taking the mean of that's okay. I'm calculating the mean of minus 1 the whole squared. So what I'm doing is I'm first creating a new variable which is actual minus predicted divided by predicted. So here I'll put a square. So you'll notice. So here it's the same as taking the mean of the actual deaths minus the predicted deaths divided by the actual deaths into 100. Okay, divided by actual deaths into 100. So this is basically a mean. It's a test of the accuracy of the model. And I can. This is not required. Okay. So I have a percentage error of 11.08%. So this is called the mean absolute percentage error. So if you want to write me to write it the conventional way, then I can just put it at this minus this. This minus this. Slash this. So it's deaths minus predicted deaths. The whole squared. So one bracket, two bracket. So you can see it's actual deaths minus predicted deaths divided the whole square and the mean of that. 1, 2, 3, 2, 3. So it's created some error. So I'll stick to the earlier one. So there's 11% misclassification of the model. Yes, I'll use the simple. Yeah. So it is deaths divided by predicted deaths minus 1. So it tells us the extent of deviation. We say the extent of deviation is 11%, and that way we try to build the model a little further to give us a better result. So the important thing is the model has a problem of heteroscedasticity, which we have not addressed in the study, and it has a problem. It does not have any multicoordinatory problems. The coefficients are the number of deaths depend on the number of confirmed cases of coronavirus, and latitude does not have it has a significant effect, but it tends to increase very high at a higher. It tends to increase as the latitude increases beyond 24. So when you look at the data, that is very clear. So if I do when I do a plot, which you've seen already, when I do a plot of the data itself, df dollar lat is on the x-axis, comma df dollar deaths. Then we get a clear that as the latitude increases, the deaths increase, and deaths are really increasing beyond this. You can see that deaths are increasing. So if you take 10, this is 20, 10. If you take 10, so you have a minimum minus 40, maximum 100, so you have 120 and 120. So let's see. So if I take the range of latitude, I can say it varies from minus 41 to plus 71. So the range, we can get the range directly. So if we have 41 minus, that is what, 110, if I have at 10 degrees latitude, at 10 degrees latitude, okay, I can have a 10 degrees latitude. I can come back to this and use the digitization option, which we discussed earlier. Okay, I can come to this digitization option and say digitization to compute equal frequencies. So I can use this option called bin. And then try to create a bin and continue that further.